All right, today we're going over 8.1, exploring exponential models. So let's first take a look at an exponential function and what the form would look like. So here's the form right here where it actually should be y equals a times b to the x, where your b is in parentheses because you're not going to multiply them first. You would do the exponent first. And x is a real number. A cannot be 0 because if a is 0, it'd make this entire equation 0, and then it would just be y equals 0, which is a horizontal line. B has to be greater than 0, so this base right here has to be greater than 0, and b cannot be 1, because if b was 1, 1 to any power will still be 1. All right, so let's look at when we have an exponential growth and exponential decay. So we're still using the same equations here of y equals a times b to the x. And if b is greater than 1, it's going to be an exponential growth, which will therefore look like something that's growing exponentially. So if it's in this form, we're going to have a couple of things here. We're going to have a horizontal asymptote, which will be at y equals 0. We're going to have the value of a is always going to be your y-intercept. And then we'll be able to look at the value of b, knowing if it's growth or decay. So if we have exponential growth, it's going to be approaching your horizontal asymptote, which is y equals 0, and it will be growing exponentially. And this is what exponential growth will look like. Moving on, if we have exponential decay, hence the decreasing here, then we'll still have the horizontal asymptote at y equals 0. We'll still have our y-intercept will be a. But now we'll just be decreasing here, where we'll be decreasing and it will still be approaching, sorry for the bad graphs here, it'll still be approaching our y equals 0 line asymptote. Okay, so let's try and plug in some values here where we can plug in, and we're going to graph y equals 2 to the x. So we know that your b is a 2, and when b is greater than 1, it's an exponential growth. So we should already have a good idea of what this graph should look like. So we can plug in some values here. We can plug in, say, -4, -2, 0, 1, whichever point you really want, but plug in some negatives, 0, and some positives. Let's plug in 2, we can plug in 3. Okay, so we have 2 to the -4. So we need to remember exponent properties, where if I have a negative exponent, I bring it down to the denominator, and then I can simplify. Anything to the 4th power is the same as squaring it twice, so this will be 16, because 2 squared is 4, 4 squared is 16. If I do 2 to the -2 here, that will be 1 over 2 squared, which will be 1/4. Anything to the 0 is always equal to 1. 2 to the 1st is 2. 2 squared is 4. 2 cubed is 8. So you can go ahead and graph that. We have -4, 1 over 16. That's about right here, about. -2, 1/4. That's about right here. 0, 1, right here. 1, 2, 1, 2 is about right here. 2, 4, and 3, 8. Okay, so we can see that it's starting to grow very fast. And, all right, I'm going to apologize for my graphs already. Still hard to use this tablet here. And then it will be approaching your horizontal asymptote still. Okay, so we still have that horizontal asymptote of y equals 0, and you can go ahead and draw that in there, of y equals 0, and that's it. That is our exponential growth. Okay, we can try one more like this. It's very similar, except for now we have the value of a, which is going to change our y-intercept. So we should still make a chart here, x, and then we can plug it in. So we have -4. When I plug in -4, I get 4 times 2 to the -4. And I know that when I have a negative exponent, I only bring the part that is negative, that has the negative exponent, down to the denominator. So I have 4 over 2 to the 4th is a 16, which is a 1/4. Okay, I can plug in -2 here. So I have 4 times 2 to the -2 is going to be 4 over 2 squared, which is 4 over 4, or 1. Oops. Okay, I can plug in a 0, and anything to the 0 is a 1, so I have 4 times 1 is a 4, and I already knew that my y-intercept was going to be 4 because that's the value of a. Okay, I'll plug in a 1, I have 4 times 2 to the 1st, 4 times 2 is an 8, and so on. So I can graph that, -4 1/4, about right here, -2 1, 0 4, our y-intercept 0 4, I can label some points here, 1 8, and so on. And then you'll kind of sketch that here. And it will still be approaching your horizontal asymptote of y = 0. Okay, we can now look at, if we are looking at the population growth, and we're looking at the rate of increase or decrease, r. So in order to find what that is, we're going to use this simple formula, which is b is equal to 1 plus r. So when b equals 1 plus r, we're going to substitute in b equals 1 plus r, and then we can find what it is. So we can say that our growth or decay factor will be b. So let's write that in there. Growth or decay factor will be b. And then we also know that r is going to be your rate of increase or decrease. That's going to be what r is equal to. Okay, so if we look at this problem here, we first need to remember how to convert from percentage to decimal. So if we look at that, we know that we are going to move the decimal 2 spots to the left. So 1.24% is the same as writing 0.0124. And that's going to be our rate, r. So it's saying in 2000, the U.S. population was about 281 million. And the annual rate of increase in the U.S. was about 1.24%. So we can find a couple of things here, which are going to be to find the growth factor, which will be b, and we're just going to plug that into our equation here. 1 plus 0.0124. So that's b is equal to 1.0124. And then we'll plug it into our equation here, where we're going to write an equation. It says let x equal the number of years after 2000. So if it's the number of years after 2000, then we therefore know that the value of a is going to be your original population in 2000, which is 281 million. So if we're doing x is the number of years after 2000, that means that at the year 2000, x would be 0, and therefore the value of a will be 281. So this will be 281. We just found b, which is 1.0124, using that equation, b equals 1 plus r. And then we're just going to plug this in to y equals a times b to the x, where we get y is equal to 281 times 1.0124 to the x power. And that will be your equation for this function. All right, moving on. We're going to write an exponential function when we're given 2 points. So let's say we're going to do this one here. I write an exponential function, y equals a times b to the x, for the graph that goes through the following points. So since our equation is y equals a times b to the x, we're going to plug these in. So we have our y is 4 is equal to a times b squared. And plugging this one in here, I'll have 16 equals a times b to the third. So it's always going to be easier to solve for a in this case here. And we have 2 equations, 1, 2, and 2 unknowns, which are a and b. So we're going to solve for a and b, and then we'll plug them back into this equation here. Okay, so I'm going to solve for a in the equation that has b to the lower exponent. So this one has b squared, this one has b cubed. So I'm going to divide both sides by b squared here, and then we can cancel this out, and therefore a is equal to 4 over b squared. Then, since a is equal to 4 over b squared, I'm going to take that and I'm going to plug it into my other equation. So that will leave me with 16 is equal to 4 over b squared times b cubed, which is the same as writing 4b cubed over b squared. Which also means if I have the same variable here, b and b, as my base, and I'm dividing, I'm going to keep the base and subtract the exponents. 3 minus 2 is a 1. So this is b to the first, which is the same as b. And then I'll just divide both sides by 4 and get b is equal to 4. So b is equal to 4 here. And then I can plug b equals 4 back into this equation here and find what a is. So a is equal to 4 over b squared. Plugging in my b, which is 4, I get 4 squared. That's going to give me a equals 4 over 16, which will reduce to 1/4. So now I know a, I know b. I'm going to now plug it into y equals a times b to the x, which will therefore be y equals 1/4 times 4 to the x power. Make sure you do not multiply a and b. Only b is to the x power and a is not. So therefore you cannot multiply a and b. And this would be your equation. You can also check it by plugging in the 2 points that you were given. And when you plug them in, 2, 4, and 3, 16, then into this equation, that should work out. Okay, moving on here, we can look at finding the annual percent increase or decrease at the function models. So this is going back to that one equation of b is equal to 1 plus r. And this is in the form of y equals a times b to the x. So we know that b is 1.63, which is already telling us that this is an exponential growth because b is greater than 1. So since this is an exponential growth, you know that your rate is going to be a positive because it's increasing, hence the growth, exponential growth. So when I plug this in, 1.63, then I can find what the rate is by subtracting 1, and I get 0.63 is my rate. Moving the decimal 2 spots to the right to convert it to a percentage, I get 63% increase, because it's a positive, is going to be our rate. For this one here, we know that b is equal to 1/4, or if you would prefer to write it as as a decimal here, then you can write it as 0.25, and then you'll plug in the same equation. Here, since we know that b is between 0 and 1, we know this is an exponential decay. So now I know that my rate is going to be a negative number, and therefore it will be a decrease. So plugging into b equals 1 plus r, I get 1/4 is equal to 1 plus r, subtracting 1 from both sides, and then I get r is equal to negative 3/4, or if I want to write this as a decimal, negative 0.75, which would be 75% decrease, and it's a decrease because of this negative, and that's your rate. And that's all for today. Thanks for listening.